Hello, my name is Dibei Chen from Tsinghua University. This talk will present CATCAM, a constant-time alteration ternary CAM with scalable in-memory architecture. Motivated by the TCAM updating problem, we redesigned the update mechanism for conventional TCAM with the emergent processing memory technique and built a prototype chip to validate our idea. A main advantage brought by software-defined network is dynamic network reconfiguration with frequently updated fine-grained rules. How fast network states can respond to network events is vital to a wide range of network functions and services. However, today's hardware switches only support less than 100 rule updates per second. On the contrary, software switches running on commodity servers handle rule updates at a much faster rate, but remain 2 orders of magnitude slower in terms of packet processing. Recent measurements on commodity hardware switches report rule installation latency up to milliseconds may cause inconsistent network states, even periodically or randomly stop responding to network events. Packets may drop or be forwarded incorrectly, while security concerns arise. The reason is that modern hardware switches broadly utilize ternary content-addressable memory for packet classification due to its match flexibility and search capability. Since the ambiguity of wildcards may cause multiple rules to be matched, TCAM stores rule sets in decreasing order of priority and uses a priority encoder to detect the match with the highest address in O1 time. However, to maintain such priority order, the insertion of a new rule could lead to a substantial amount of moves for stored entries. It incurs ON costs in the worst case, where N is the number of the existing entries. Most TCAM updating algorithms exploit rule dependency to minimize entry movements, but incur prohibitive computation time since they are still based on the premise of the same priority encoding scheme. This paper proposes a constant-time alteration ternary CAM that can accomplish both lookup queries and update requests in O1 time. The insight is to decouple rule priorities from physical addresses. To this end, we propose a matrix-based priority encoding scheme so that new rules can be inserted without the shuffles of the existing rules. The interval-based scheduling logics can help scale out and guarantee deterministic update performance. CATCAM is made possible with the PIM technique of ATSRAM. The prototype chip achieves at least 4 orders of magnitude speed-up over state-of-the-art TCAM updating algorithm, while incurring 16 energy overhead and 75 area overhead. Note that these numbers are slightly different from the original paper, which will be explained later. To decouple rule priorities from physical addresses, a straightforward way is to store the priority of each rule and select the one with the highest priority during lookup. Since rule sets typically contain thousands of rules, implementing such comparison at low cost is unrealistic. Instead, our scheme encodes the priority relation between rules in a priority matrix. Each rule in the match matrix, which is an alternative to conventional TCAM, correlates with a row and a column in the priority matrix. A Boolean element is true when the corresponding rule of a row has a higher priority than the corresponding rule of a column. During lookup, the priority matrix is traversed to filter out the rule with the highest priority. We leverage the insight that if a rule has the highest priority among all matched rules, its priority has to be higher than any other matched rules. That is to say, for any other matched rule, the Boolean element in the specific column should be false. Therefore, for each matched column, iterative NOR operations are performed on matched rows. The resulted one-hot report vector indicates the rule with the highest priority. Since the priority order is no longer associated with rule addresses, new rules can be inserted into any available entry in the match matrix. Its priority is compared to those of stored rules to update the corresponding row and column in the priority matrix. As a result, both lookup and update in the matrix-based priority encoding can be completed at O1 cost. To scale out, large and complex rule sets are partitioned into multiple subtables. Since the entire priority range can be segmented into a series of non-overlapping intervals, by storing rules whose priority belongs to a certain interval in a subtable, the priority relation between subtables can be encoded in a global priority matrix. Intuitively, the highest priority rule must be among the highest priority subtable. To perform lookup, matching results from each match matrix are collected and arbitrated by the global priority matrix, then chooses the local priority matrix to perform the priority decision. The priority intervals are determined by the highest priority rule in each subtable. For an incoming rule, its priority must belong to one of them, and the associated subtable is the one to be inserted. In light of different scenarios, the interval-based scheduling logic is proposed for rule insertion. If the subtable to be inserted is available, the new rule can be safely inserted into any available entry. If the subtable to be inserted is full, the highest priority rule in it is reallocated to a subtable whose priority interval follows to make room for the new rule. The priority relation between these two subtables is kept, and the new highest priority rule can be obtained by assuming all rules in a subtable is matched. What if the following subtable is full neither? A naive approach may lead to iterative rule reallocation between neighboring subtables until an available entry is located, which again incurs O(n) cost, where n is the number of subtables. Note that the priority matrix decouples subtable priorities from physical addresses. Therefore, in this case, an empty subtable is assigned to accommodate the evicted rule. Its priority should be between the current subtable and the one that follows, and the global priority matrix is updated accordingly. CATCAM can thus scale out to hundreds of subtables. Given that at most one rule reallocation is demanded, rule insertion can be completed at O1 cost in any scenario. The priority decision in the match matrix involves massive logic operations. Luckily, enabled by the processing memory technique in ATSRAM, where multiple word lines are activated simultaneously, no operations between activated words are performed in the shared bit lines. In this way, each priority matrix is mapped to an ATSRAM array. To perform the priority decision, the match vector is applied to the priority matrix. Associated read bit lines are precharged first, then activating associated read word lines. The results are detected through sense amplifiers. In addition, a dual voltage write scheme is adopted to directly support column-wise write for the update of the priority matrix. Hence, both lookup and update can be fulfilled in O1 time. Here is the overall architecture of CATCAM. Each subtable includes a match matrix and a priority matrix, and is connected to the peripheral control logic. Crucial subtable metadata such as priority intervals, vacancies, along with all the priorities of stored rules are kept in the metadata cache. CATCAM also comes up with a 3-stage pipeline for lookup to increase overall throughput while reducing energy overhead. In addition to the circuit-level simulation from the original paper, we have taped out a prototype chip this May. As a proof of concept, it has 16 subtables in contrast to 256 in the paper, and each rule is 160 bits wide in contrast to 640, offering a capacity of 4K entries. Such scaling should not affect the conclusion since CATCAM features O1 performance. The prototype chip is fabricated in TSMC 28nm process. It achieves 470 MHz at 0.9 watt, while consuming 0.35 watt. We measure the performance of various lookup table tasks ranging from search, deletion to the aforementioned insertion scenarios. Rule reallocation takes more cycles since one of the existing rules has to be read out then reinserted. According to further benchmarking, around 80% of update requests can be accomplished without rule reallocation or subtable assignment. CATCAM is compared to state-of-the-art TCAM updating algorithms with ClassBench. It generates various types of rule sets with different sizes, and rule insertion and deletion account for half each in the update stream. As can be seen from the diagram, CATCAM achieves an overwhelming speedup between 4 to 6 orders of magnitude. For previously dependency-aware algorithms, the compilation of minimum dependency information is complicated and time-consuming, especially for large rule sets. In contrast, the algorithm architecture co-design of CATCAM eliminates such overhead and guarantees deterministic performance that is not subjected to rule set characteristics. Compared to its match matrices, CATCAM incurs 16 energy overhead and 75 area overhead. Since the concept of CATCAM is also compatible with the existing TCAMs, it could potentially benefit from more area or energy efficient TCAM design. This is the end. Thank you for your time.